Well, finally, we are getting to precast concrete, my favorite subject. Looking at all these precast concrete parts that are very commonly used in the industry just brings back great memories for me of my youth. What is precast? Precast concrete is a construction product produced by casting concrete against a reusable form in which it is then cured in a controlled environment, often transported to a construction site eventually, and then you maneuver it into place with a crane or some other heavy equipment. That's, of course, very heavy, so you've got to use heavy equipment almost always. So examples would be beams and wall panels, floor panels, roof panels, and even piles. So casting precast concrete in a dedicated plant makes things much more efficient. You get higher quality control compared to trying to do these things out on a job site where you don't have everything as organized and well suited. Steel forms are very, very often used in precast concrete. They can use them thousands of times to pour more pours or more products. So, of course, when you're looking at these items, these are pre-stressed items. All of these, double T that's swinging in the air and the columns. So very often with large products, they are most often pre-stressed items also. So what is pre-stressing? So pre-stressing, well, it can be pretensioned or post-tensioned. Both are a form of pre-stressing. So with pre-stressing, this diagram is looking at basically post-tensioning, but if you look at the very top beam here that I've got my cursor swinging around on, that's just got rebar in it. And the problem with rebar is it's dumber than a doornail, doing nothing until the beam starts to bend, and then there'll be micro cracking going on. So of course that means you have to add a lot more rebar to keep the cracking to a minimum, and there are limits to how far you can go with rebar. You need a certain amount of concrete around each piece of rebar in order for it to develop strength and bonding and everything else. And so you can only go so far with rebar. And that limits the size of your beams or how much load they can carry. So over on the left side, we're looking at the idea of where the rebar needs to be. In the top of the beam, when it's a cantilever, when it's dangling out. But predominantly, the rebar needs to be down in the bottom of the beam when you're going from point A to point B, like we have in this main beam that I've got my cursor around. So then the second one down is what happens when we do post-tensioning, is that we have the pre-stressing strand, the tendon, is in a tube or a sheath of plastic, and it's running through the whole beam when you pour the concrete, and it's loose in there. It's just held in place so that it's nice and straight where it needs to be, or whatever the positioning is. And it might have an anchor embedded into the concrete at one end, but you're at least going to have one end of that pre-stressing strand sticking out where they can grab a hold of it with a jack. Now they're not showing the jack in this picture, but then you can, so once the concrete's strong enough, so on a normal job site, you can do post-tensioning. You can literally, pour it inside the concrete. And once the concrete's strong enough, then you can push against it with a jack to stretch that strand out. So that's what we're kind of seeing. And it's literally, if you have it in the bottom of a beam, if you get enough post-tension cables going, you can actually compress the concrete enough with these that it's actually causing the beam to have a crown in it, where it can compress more on the bottom and it's in tension more on the top and get a crown in it, just like sometimes you can see in wooden beams. When we're setting up a 2x12 or a big heavy timber, if there's a crown in it, we typically want the crown to be up, the curve to be up, just like this beam. And then when you get the load on it, then the idea is that would level it out again. And so that's the whole calculation of how much tension you want, how many pre-stressing strands, and all of that. Anyway, so the act of having steel that's already under tension, that means it's already actively holding the particles together in the bottom of the beam before there's even a load. And so it's much more dynamic, can support much more load, And so that means you can have beams that are much, much longer, more slender, and can carry heavier loads. And that's how we're able to do modern precast concrete at a level where we end up with tremendous spans in concrete and do defying acts with concrete that you just wouldn't otherwise be able to do. Okay, so we're looking at post-tensioning in this diagram. Here, we're looking at pretensioning, something that we do in a prestressed concrete plant. If I ask you in a test question, how much, where can you do pretensioning? Predominantly, you can do that in a prestressed concrete plant. You really can't do that easily out in the field. You'd have to have forms that are so strong that you can use them to stretch out the steel pre-stressing strands. It's kind of like a giant guitar. You got the guitar strings have to have the structure of the guitar neck and the bridge and the whole structure to hold the guitar strings in place. And so these pre-stressing strands will be out in the open under full tension. You can literally play notes by tapping on them. They'll be so high in tension. It'll be very much like a giant guitar. And then we pour the concrete around those strands, and when the concrete has gotten to the correct strength, it's then bonded well enough to the pre-stressing strand. Then you can cut the pre-stressing strand at each end of the girder or the beam or whatever the element is, and then you impart a compression in that beam in the same way you do with the post-tensioning, but you can do it much more efficiently. With post-tensioning, you most often end up having to have custom-made cables with an anchor built on one end and a tail sticking out, and a bunch of hardware that you deal with there for each individual beam. In pretensioning, we often might have a form that goes 600 feet or something like that down the line, and you have a whole bunch of beams in line using the same cable, so you get some efficiency by putting a whole bunch of beams in the same form, a long form, and you just have bulkheads dividing them up all the way through it. Okay, so I'll just elaborating a little bit here. So this is the post-tensioning model again, just in another diagram, but it's showing that the idea, you've got to have ducts, as they call them, not a quack duct, but DUCT, duct. And that's not what I would normally call it. We would call them tubes or jackets that the pre-stressing strand is in. It's the same kind of strand, but in post-tensioning, they will generally coat that pre-stressing strand with grease and then put it in the jacket, because we definitely don't want the strand to bond to the concrete there, because we're relying on an anchor and a chuck fitting at one at each end, or both, having a chuck fitting where we can pull it up at tension and secure it in there, embedded in kind of a pocket. Okay, so here's a diagram that kind of shows you the idea for post-tensioning, how we end up with this hardware that gets installed up against the form out in the field, and the pre-stressing strand, it might be drooped or it might be straight depending on what the needs are, across and chaired up to be in the middle of the concrete. With the pre-stressing or post-tensioning that we do for a house slab or a slab on grade, then we put many of the pre-stressing strands end up in the center of a 4-inch slab, and so then they're equally in the center. Whereas for the pre-stressing strands, the post-tension cables that are in the thickened slab, the footings, the perimeter perimeter footings that are all and various other grade beams, we would often have it droop down into the footing and back up where it can. So we get a similar process, but yeah, some of it will be in the center of the slab, equally compressing both directions, and so then there won't be a crown there. But anyways, I've got some pictures later on here I can show you on this. Okay, there are other kinds of products besides all of these glorious large beams and girders that I was talking about and showing pictures of. There's precast industry that's all around smaller stuff like septic tanks, water tanks, catch basins, manholes, utility vaults. There's parking curbs that are even smaller, and maybe even little patio blocks in Home Depot. There's precast picnic tables and precast concrete benches, and there's garbage cans that or you made it a precast, maybe with exposed aggregate, kind of like this one, this table has on it, for decorative architectural concrete parts. And that's, of course, at a much smaller scale. None of that is pre-stressed in any way. They wouldn't do that. Just they would rely on smaller stuff. They're going to rely on regular rebar and even mesh. They have some heavy, heavy mesh that are often used in some of these septic tanks and stuff. Okay, now we're looking at maybe the most common heavy-duty beam, a girder, really. When they get to be the big honking beams, we call them girders. It's all a matter of relative size, but the most common one is for large heavy-duty use would be the AASHTO beam, AASHTO beams. And of course, that AASHTO abbreviation stands for the American Association of State Highway Officials. I talked about that way back in chapter 1 in this course. But the AASHTO beam is this big chunky I-beam, basically. And there's a whole bunch of possible pre-stressing strands. You see them all showing up in this picture right here. They're all sticking out because we often will take a cutting torch to cut these strands initially, and then we'll grind them off flat, like you see in the next beam. And you're actually seeing some of the grinding against the concrete. And then they'll coat them maybe with an epoxy or with some other kind of maybe a non-shrink grout mixture to kind of clean it up and make it look pretty. One way or the other, it's amazing how much patching can end up happening on some of these precast girders to make them look nice. You can patch up everything from the septic tank and everything else, and by the time you get finished, you're not going to tell the difference that it had been patched. Any flaws can be fixed up if you need them to be. So, as I mentioned, this is showing up an indoor pre-stressed concrete plant where they actually make hollow core slabs. I'll have to show you an example of that first. But just a couple of things in here. We very often in precast concrete will use type 3 high early cement in the concrete mix in order to speed up the setting of the concrete, so that and maybe steam curing, especially in wintertime climates. You wouldn't need to do that in the summer so much, but it keeps the concrete moist. But more importantly, in cold weather, you need to keep the concrete warm. By the time we get to the Louisiana summers, our problem isn't trying to keep it warm. We want to keep it from getting too warm. But high early strength is used a lot in the industry for precast, so that they can get that part picked up and out of there so they can form another part. It increases production. So the last sentence down this page is what I've already kind of described, but it says pretensioning is usually performed off-site at the manufacturer's plant. Cast in place concrete on-site concrete is rarely pretensioned because you'd have to have the form to do it, but you can certainly do post-tensioning on any site. So post-tensioning is something you're going to see more of in your experience. Okay, and here's some more pictures of the same kind of idea with the pre-stressing strands stretched out. Here we've got the hollow core slabs that I was talking about, and there's one being picked up by a vacuum pump. They're literally a glorified suction cup system, so they can pick up this slab and place it right up against the other hollow core slab that they're standing on right now. They typically want that to be butted up right tight to it. And so that's why they need a vacuum pump. Whereas a lot of times when you're picking up these hollow core slabs, otherwise they have a lifting clamp that grabs a hold of the keyways on each side. A little kind of a complicated key jointed system on the edges, and in order to grab a hold of the thing. Whether it's a vacuum pump or grabbing it by the keyways, you don't want your toes underneath that no matter what, because there's always a chance these things can drop. The hollow core slabs are used to build floor systems, precast floor systems. So you'll see more examples of that. So now we're going to be kind of looking at the precast structural elements. And what I mean by that is basically the various kinds of standardized precast concrete members that are used to build buildings and bridges and everything else. So in this background picture, you're seeing solid flat pretensioned slabs. So most of these parts are going to be pretensioned, whether pre-stressed or precast, but prestressed, but mostly it's the pretensioned variety of prestressed as opposed to post-tensioned. Okay, but there are exceptions. Okay, so let's look at this list here. You're seeing a field full of precast out here at a precast concrete plant of some sort. And in that field, there's going to be some, number one, slabs. They're seeing a lot of slabs out there. Slabs, generally we call them slabs when they're going to be horizontal. They're going to be floor systems or roof systems, roof panels or floor panels. The next category is beams and girders. And so the beams and girders generally are going to be supporting those slabs. And then there's columns that could be supporting beams and girders. So that's number three. And then the fourth one would be wall panels. So they can be slabs too, but we don't call them slab. When they're panels, they're generally vertical. And so generally when you look at these flat slabs that are horizontal in this picture, those are floor or roof slabs. Whereas these panels that are vertical, those are generally wall slabs. They will generally store them vertically because they don't tend to make them strong enough to be held horizontally. They could be, but maybe not. So that's another trick that can tell you whether it's a floor slab or a wall panel. But in this category of slabs, there's something called a double T and a single T that are in the category of slabs sometimes, but they can also be beams and girders. So there's some that cross over the line between the two, blurring the definitions here. So I'll show you some samples. But one thing I want to mention before I leave this page is that down here I've got kind of a point or note at the bottom in the blue at the bottom. It's talking about the connections. How do we connect all these parts together? Well, we do that by bolting them together sometimes, welding them together, post-tensioning them together, or grouting. So maybe I should change the order of this a little bit, but the bolting and the post-tensioning are kind of a variation on a theme. If you've got tubes, cavities through these that you can fish some post-tension cable to put them, string them through some concrete parts, and then you suck them up tight with post-tension cables. Well, that's kind of a variation on a theme of bolting. It's just that you're using pre-stressing strand to do it. Whereas welding, you've got weld plates that are embedded in the concrete slabs and beams and girders and columns and wall panels that have to match up so that you can weld the concrete parts together. And then grouting is sometimes used to pour across and connect a bunch of parts together with, and I'll have to show you some pictures of that. But the grouting is also used to protect areas where they've been welded to keep the weather away and protect them from the elements, like salt on a road and that kind of stuff that can rust them. Okay, so now let's actually look at some samples here. This page, we're looking at the category of the first one, dealing with precast concrete slabs. These are going to be floor slabs or roof slabs. And generally the difference between the floor slab and a roof slab is just how strong it is. The floor slabs have to be stronger. We expect floors that we walk on to not bounce around like a all-star wrestling trampoline. We need it to be rigid so that your coffee doesn't rattle off the table as you walk across the room. And so the floor slabs are going to be stronger. So as you're looking down here, we've got solid flat slabs. They're not as strong as hollow core slabs, even if they're the same thickness and everything, because the solid flat slabs are heavier. That's solid concrete. Whereas the hollow core slabs, what they do is they have these hollow tubes running through them here, hollow cavities, basically, all the way from one end to the other. They're formed that way right from the beginning, which removes a whole bunch of unnecessary weight that doesn't really add to the strength of the concrete. So they're making it lighter weight, but they've got the same kind of reinforcing that the solid flat slab. That's what makes them stronger. So that's why hollow core slabs are stronger than flat slabs. If you're looking across this page, we're going from stronger to weaker as far as how much load they can carry, how far they can span, that sort of thing. The single T is stronger than a double T, which is stronger than a hollow core slab, which is stronger than a solid flat slab. So that's an important test question to remember. Remember that the stronger ones are the deeper ones, and that's going to be over here. The single T's there's no point in making a single T unless it's huge, because they have to be cradled. They don't stand up on their own, so they have to be held in a truck. They'd have to be sitting in a cradle, whereas a double T stand up just fine. A hollow core and the solid flat slabs, they can sit down in a truck with some dunnage underneath them, be strapped down and be fine. So the single T is a lot more work to care for it and stand it up and place it somewhere, anywhere along the way. And so they only make single T's when they're big. So even though they're talking about the 8 and 10 foot widths here, that's not completely true. The single T is going to be wider than that. Okay, so these are the slabs. But that said, double T's are often, and single T's are often used as big beams too. No, mostly standalone beams, so that's why you'd call them. But you could build a whole bridge by just putting a bunch of double T's together, or a whole parking structure. It could be the whole floor system, but they've got little ribs here. The bottom of the T, the stem of the T, is a beam, and so that makes them stronger. Okay, so here now we're looking at pure beams and girders. They're never used for anything else but for beams, and of course, if they're big and honking beams, we call them girders. And so the Astro beam is maybe a girder, and the rest of these might just be called beams, but they're all beams. Okay, so you could have a simple rectangular beam. That's what we have on the left. The next one over is an L-shaped beam. Then the inverted T is a T upside down. The whole purpose, though, is that you could take a double T, like we had back here, and sit it on this ledge right here, and on this ledge, further apart, of course, and the idea is that then the top of the double T is sitting on this is matching with the top of this L-shaped beam. And then this rebar that you see sticking out of here can be sticking out, and then you pour concrete across the whole surface of the bridge deck, and that gives you, or a floor deck or whatever, and that gives you concrete that's connecting the double T, which might have a real rough finish on the top, so that it can bond better to it, to all the concrete, and all this rebar sticking up, and that helps the beam to. This becomes a joining system. So I'll show you some pictures of that in a little bit here. Okay, and then there's one other category, besides the Astro beam, which is big honking thing, or all these beams, and that's a box girder. And they almost always don't call them box beams. I guess some people do, but yeah, it's a box beam. But the only reason they build a box girder is to make it massive. So a box girder could be an entire lane on an interstate overpass going around for somebody that's changing in a cloverleaf intersection on an interstate or something. It could be the whole lane right there. You can tell how heavy this is by just look how many tires there are. It looks like there's, I don't know how many count, but there's hundreds of tires on this sucker. So it's carrying a heavy load. Now a box girder or a box beam has often a hollowed out area like this, a big hollowed out area in the center of the beam. And a lot of times it's not even open. They can actually frame it up with wood and just leave that wood in there and ignore it. They don't care what happens to the wood inside the beam, but it's lightening their box beam. This one is open through and through, but it wouldn't always have to be. Okay, so that's a box girder. Now here we've got the inverted T right here, where I've got my cursor. So it's got a ledge on this side, a ledge on that side, and then we've got the L shape over here, the L beam. And so they both have these ledges that you could then sit those beams in. And they're sitting on top of columns that have corbels. So this little ledge and that little ledge down here that these other L-shaped beams are sitting on are called corbels. But there will be a piece of angle iron embedded in this column right in line with the top of that L-shaped beam, which will also have a piece of angle iron or metal plate that's embedded in the concrete. In both cases, it's not just a piece of metal embedded in it. It's got to be welded to some rebar tentacles going back into the concrete. And out of that, they're able to weld those two pieces together. They will also sit this beam down on that corbel, but with a little rubber pad, a high-grade neoprene rubber that might be, well, depending on what size, might be 6 inches by 12 inches wide or something. But the idea is it's kind of like your mouth guard. If you have trouble grinding your teeth at night, you might get a mouth guard that you wear so you're not grinding your enamel off your teeth. Well, the rubber, the neoprene rubber, is meant to keep from rubbing away at the surfaces of the concrete over the years in any movement that's going on. And it's very, very, very common to use these rubber pads. Not very common to have just concrete against concrete part. Not done very often. Okay. Here's a whole bunch of columns here. And then you see some wall panels in the background. So I'm basically dealing with wall panels and columns. The wall panels can be used as columns to support some of these beams. You see kind of some little rectangles in the background. Those can be beam pockets that are meant for a beam to sit in there. And they all would have those weld plates embedded in there for that purpose. Here's some more wall panels here in both those pictures. So again, the wall panels, you can typically see that they're standing leaned up in a cradle of some sort or standing up. They don't just lay them flat unless they're really heavy and thick. You know, if they're thick enough and strong enough. I remember having some so-called wall panels that were really bridge abutments, and they were 12 inches thick. Well, they were so darn strong, it didn't matter how you laid them, so that didn't matter. But a wall panel that's only 4 inches or 5 inches thick, you're going to cradle them properly. They're not going to be strong enough to want them to lay down. Okay, I digress. And then there's other parts. You can have precast stairs. I didn't mention that in my list earlier. And you see some more hollow core slabs standing up over here. Hollow core slabs are maybe the most common item. They're just so efficient in the use of concrete for floor slabs and stuff. Okay, and other parts in here. Here's a building that's all being put up with a whole bunch of wall panels. There may be some columns in there that I'm not seeing, but it looks like everything is connections by panel to panel, like a house of cards, except they're much, much stronger when they're all braced up here. And then down below, you're seeing double T's that are sitting on wall panels, on corbels that are installed in wall panels. But again, it wouldn't just be sitting there on that little ledge. It could slip off of there, so it's got to be welded at the top. They generally rest on something at the bottom, and they have a weld plate where the two pieces are welded to each other. And then the two double T's, when they're fitting against each other, lengthways beside each other, there's usually a keyway pocket where the weld plates are joined every so often, maybe every 8-12 feet apart along the length of the beam. Again, the double T. So those double T's get welded to each other also. So a lot of welding goes on with precast parts. Here's some double T's right here in a parking structure. And if you ever get a chance to go to walk around inside of BRCC's parking structure, I'm getting used to doing that. Up in Canada, we call them parkades. So I don't know, maybe in the States there's some places too, but people look at me weird when I say that down here sometimes. But parkade, okay, a parking structure. Okay, that's a lot more syllables. But anyways, our parking structure on campus is made up of a whole bunch of double T's. And so if you ever get a chance to walk around in there, you'll see them from above and below and stuff. And you'll see the keyway joints that have been filled in with a non-shrink grout. So that's an important thing that will be turned into a test question in this chapter too. Is that a non-shrink grout is not, if I ask you true or false, a non-shrink grout has absolutely no water in the mix. That's absolutely false. There's always got to be water in any concrete mix, including a grout mix. Even a non-shrink grout mix. It's just that we would mix in some aluminum powder to make it non-shrink, but we would also want it to be zero slump mix for something like that, because we call it dry pack because we're literally packing it oftentimes with pieces of 2x4 and beating it with a rubber hammer into the pocket where the grout is going to fit, and then it's smoothed out with rubber gloves on and stuff. Anyways, the manufacturing of these elements, just show you a little bit of an inside of this building with the process. So here, this long bay here, they probably have a steam unit they'll turn on when they're finished. If it's wintertime in a cold climate, they'll have, and when you have it indoors, that's usually the reason why. Each one of these lines they make hollow core slabs in. And so there's spools of pre-stressing strand right here on the end here, where my cursor? Let's see. I think go in a little bit closer. Yeah, so you can see the same picture, but blown up a little bit. So these are pedestals right here and here that they pour on top of, but they pour these hollow core slabs with a zero slump concrete mix, meaning, and the reason for that is they don't have any form. It's sitting on a pedestal, but they're using this machine over here to shape it. So they literally have this track right here that's running around here, and they got this device that rolls along the track that they pour concrete into a hopper and fills up this machine that vibrates and shapes the concrete into the hollow cores, including the tubes that you see here, the hollow tubes that are shaping up here. And they just make one long, really long hollow core slab that's running the whole length of the building on these pedestals. So they've done that here. They're making one right here. There's nothing over here. They're shaping. They're on their way, buildings. And they've already stretched out the pre-stressing strands here, but they're not under tension. They're just laying here. But over here, they would be under full tension up above the floor. And they're you want them in the bottom quarter of the beam, is where they put them. But anyways, this is hollow core slab forming. And then they'll go and they'll take a big saw later on that they'll run on that same track, and they'll saw cut and cut it to the length that they need it. So they actually make these hollow core slabs full length, and then they cut them. Well, when they cut them, they'll cut the strands at each end first, but they'll cut them to the exact length that they need all the way down. And so they will have thought that through throughout the whole process, of course. Anyways, so eventually they'll do these two also. Here we're looking at the guts of a ashto girder, an ashto beam. So what happens is they don't have the side forms on here. Now they don't do this in zero slump concrete. There will be this precast stuff will be in a high strength concrete mix, more than 6,000 pounds per square inch compressive strength, 7,000 up maybe to 10,000 pounds per square inch compressive strength. But a lot of it would be in the 7,000 or 8,000 level, at least over 6. And so we're looking at a whole honking bunch of pre-stressing strands down here. So this must be carrying a heavy, heavy load. It's also a pretty long ashto beam. And then there's another thing. These are pre-stressing strands right here that are running down to a center part of the beam and back up. We call them harped strands, like the harp that the angel plays. I don't know, the angel, if there is one. Anyways, I'm playing. Yes, you get the idea. It's a bit of a play on the word harp, but I mean they're harped, and it's basically following another path of tension within the girder, and it's a way for them to follow that path and to add even more strength to the sucker. Now this other cable at the very top is outside of the concrete. It won't be in there, but it's holding up these rebar pre-bent stirrups that are basically been bent into this shape to go up here, and they'll be sticking out of the top, just like we saw in an earlier diagram. So giving you a lot of description here. There's that shaper that forms the hollow core slabs right here. Give you an idea of the shape. It's basically making those keyway shapes, and the concrete has got just enough water for the chemical reaction, but not enough to slough away, so it holds its shape like a piece of clay that you're modeling, And then to keep it from drying out, they'll run the steam, and that's really important when you're dealing with zero slump concrete. We do that with the concrete masonry blocks also, zero slump mixes usually. If there's a cavity or a bulkhead like with double T's, we do this all the time. We'll have a bulkhead in here, and there'll be a cavity that they'll literally use a straight-armed cutting torch and reach in there and cut the cables, cut the strands, the pre-stressing strands. Okay, let's see. Here they're picking up a hollow core slab, or in his case, they're calling it a plank. But it's with the big lifting clamps that grab it by the keyway. But what happens is that's not very practical when you're trying to place it right in its final resting place next to another hollow core slab, because you can't get it close enough. So they'll use either a vacuum pump or some very slender cables that they're kind of cradling in it. So that's not the best, but the vacuum pump is the best. Here they've got I can't tell if they've, I can't see enough definition in the picture to see what they're using to lift. If it may still be grabbing it by the keyway, but maybe this particular design has the top keyway is a little further back or something. I don't quite know. Okay. And it's very common to use spreader bars in pre-stressed concrete to pick up these girders, so you have more control. And it can be much, much longer than this for a big long girder and a much heavier spreader bar. Here's a whole artistic stack of smaller ones at the top and bigger ones at the bottom for hollow core slabs. And so, yeah, the deeper ones that have a deeper depth to the height on them, or whatever you want to call it, they're going to be able to span longer distances, carry heavier loads, and by the time you get to this light stuff, you might be, I don't know if I've ever seen one as light as that top one, but the one at the second to the top and the one down from there are probably something you might use on a roof instead, where you don't need the heavy loads, where the deflection is less of the problem. Look at the little dots. Those are pre-stressing strands in there. So the pre-stressing strand are always visible because they've been saw cut through the whole thing, you know. Okay. Joining of the elements. Well, now I'm getting back to the thing I had at the beginning of the course, or beginning of this presentation, dealing with the connections. And we're looking at the connections now. The bolting, the welding, the post-tensioning, and the grouting. So we have some diagrams in here to show you this. So a column, you can have precast columns, and they would typically be bolted together. You can see how they literally have some threaded bolts that are welded into this plate assembly that are poured into the bottom column of the lower column, at the top of the lower column. And then this plate up here would receive that, and then you could reach in here into this little cavity and put nuts and bolts in there to bolt these two columns together. But they don't typically rely on, when you do something like this, they got to protect that steel from corrosion, especially if it's at the external, in an exterior environment. And so they would put in a dry pack grout in here to make this all solid afterwards. After it's all bolted and torqued in place, somebody would come back with dry pack grout. Typically, they'll go and spray or mop in some concrete fortifier, basically white glue with a lot of extra water, so it's kind of a milky material that they'll spray or mop or brush in there, and about 15-20 minutes later, it's dry enough to dry clear, and then they can go and get a good bond with the concrete and the dry pack grout that they pack in here. And here we've got these corbels, and the beam is sitting on top of a neoprene pad. This virtual reality here, this has come out of Autodesk's AutoShade program, but it's basically showing the beam sitting on, and you can see a little black bearing pad. That's a neoprene rubber pad that the beam sits on. But then the actual real connection is done by welding from one weld plate to the other. So you see the weld plates are welded right into this cage. Most of the time, we electrically connect all of these metal plates with rebar that's all welded together in a way where you can count on it to be electrically connected. That way, the welding ground wire can be connected in one place, and you can go across and weld this stuff without having to keep moving your grounding cable. So that's just another side note here. But anyways, you can see the rebar poking up out of the beam and sticking out over here too. And all that gives you a positive connection. And then when okay, I forgot I had zoomed into the same picture here. Yeah, okay. But anyways, here we're looking at the hollow core slabs now. Sitting on the edge of that beam, you normally need at least 3 inches of bearing. That's something that shows up in the building codes and in my questions somewhere along the way in the assignments. You'll see that listed there. 3-inch bearing for concrete on concrete. But if you have wood or steel, then you only need 1.5 inches of bearing. That's a general rule in construction. 3 inches of bearing for concrete on concrete or on a concrete ledge or whatever. But if it's wood or steel, then you only need 1.5 inches. Anyway, so they got that here. It's sitting there, it's fine. But to get a connection, they literally took and tied some rebar in here, running the length of the beam inside of those stirrups that are sticking up out of the concrete beams. And same thing over here. And then they pour concrete in here. So by pouring concrete across here, some of it will spill into the hollow core slab cores, the hollow part, a little bit. They don't, some distance, maybe 12 inches in there or something. And they fill this up and even into this. Now they could also do another connection, and sometimes it's done all as one pour, where they can go and fill and cover the whole deck. Somewhere I had a cover. Okay, I don't see it here. There it is. They can just cover we have mesh on top. We might have a 2-inch topping that goes on there. And so if they do that, they typically will either put concrete fortifier down there, the glue, the milky glue that on the whole surface to get a good bond. Or if the concrete hollow core was a rough surface to begin with, then they get a good bond. They don't do that with hollow cores too much, but with double T's, it's not uncommon to have a coarse broom finish on top so that you get a better bond when you pour concrete on top of it. And again, you're seeing the pre-stressing strands are here, and then you're seeing that they'll actually have sometimes a piece of rebar. Let's see if I got that in the back in this picture. Yeah, there's a piece of rebar they can stick in as they're installing these hollow cores that's in the keyway. And so when they're pouring concrete, the concrete goes in there and bonds, so that the rebar goes and ties the two hollow cores together. So these are all integral ways of connection. So connections are done by grouting, but often it's a combination of things. Okay, and then here I was talking about the double T's and the keyway. This is what the keyway looks like if you're looking down the end of it. Well, you can't look down the end of it. You don't have x-ray vision usually, but here you can see the keyway. The keyway will be straight, but then beveled in so that it's bigger inside than it is at the top. And then we pack the non-shrink grout in to protect those welded plates. And you can see they got a chunk of metal plate. Often show up at the job site with a whole bunch of chunks of metal plate to help bridge the gap, because you got to get an electrical connection across here to weld it, and that's generally done with a big chunk of plate that might be 1/4-inch, 1/2-inch plate metal plate that they would weld across from one to the other. Now that cell phone kind of tells you that this is an old picture, because there hadn't been a phone that worked like that for a long time. That's probably a 2G phone at best. Old Nokia. Anyways, so after the two precast elements are joined, let me just read this part about the dry pack grout. The exposed connectors that aren't covered by a slab topping are usually dry packed with Portland cement-based non-shrink grout. So again, just because we call it dry pack, it's dry enough that you can touch it without getting your hands wet just about. Well, not that you should be doing that. You should still be using rubber gloves, because it will be moist. But it's going to be like a lump of clay, and you're jamming it into this hole, often with scraps of 2x4 blocking, 2x4s or wooden that you're pounding in there to pound it tight into the joint, and then smoothing it off smooth at the surface, oftentimes with that same 2x4 rubbing it across the top of the deck. Okay, and here they are taking a high slump grout that they're pumping into cavities sometimes. So that's another thing that's sometimes done. Now, the reason we know how strong everything needs to be is by testing. So this example here is looking at a test bed at a university. I don't know if they tell you here. No, they don't say. Where they're simulating an earthquake. So we understand these forces of what we need through a lot of practical experience. When we have an earthquake anywhere in the world, there's typically a team of engineers that'll travel there to investigate the accident. Well, what do you mean accident? We know it's an earthquake. We know that. Yeah, that's already known. But there's different kinds of earthquakes. Some are going to be side to side. Some are going to have a twisting action. Some will have a wave going. And a lot of times it has to do with the location of the earthquake center compared to the location of the building or the bridge. So here, at a university, they've got some double T's that are set up here on a frame of concrete, and they're shaking it with that orange strap. They're simulating a certain kind of earthquake from the structure in order to test the connections to see how well the connections work. And so this is a way of testing and sampling this. And they have sensors all over the place to measure the forces and the shaking and everything else. But very often when there is an earthquake, we learn things every single time. And so much of what we understand and know that allows us to make buildings strong enough, but also not overdo it. If you make something too heavy and strong, you've wasted a whole bunch of money. You want to use what you need, but you don't want to overdo it either. And so that's part of the science. So you'll find that much older designs of bridges and buildings were much stronger. Like the Empire State Building is probably the strongest high-rise in the world because it was the first, one of the first, or was the first to became the tallest for something like 50 years or something like that. I can't quite remember what I read on that, but it's a very, very long time before anybody ever managed to build a building that was taller or more impressive. What's impressive about the Empire State Building is just how strong it is. I doubt very seriously that a plane could bring it down. Let's put it that way. So it's kind of like the old cars, we had the old ancient cars that I grew up with in the 50s and 60s. They were tough. And so the car would survive the accident, the people didn't. Whereas nowadays we make our cars to destroy themselves and save us. It's a little different philosophy. Well, it's not like that with buildings because the buildings normally don't crash anywhere, but we have learned how to make um, buildings leaner but still be stronger. And a lot of times some of the old buildings, we didn't understand what the forces were. And so there's plenty of old buildings that might have been strong for one kind of issue, maybe a certain kind of earthquake, and maybe not survive another kind of an earthquake. So it's more complicated than that. But anyways, just a little bit about the knowledge and how we understand these forces. I mean, there's a lot to engineering these things to be strong, all these concrete members to be strong enough. And the connection, more important, are the connections between them. Most buildings and bridges and structures, when they do collapse, it's because the connections failed, not because they undersized a beam or a column. Okay, just another aside thing as we're coming to the end of this thing is that, traditional suspension bridges like the Golden Gate Bridge, you had this big heavy cable that drooped and went over to the other, from one tower to another. And then you have straight line cables coming down to support the bridge. Modern suspension bridges are what we call cable-stayed bridges. Cable-stayed suspension bridges where they have these towers and they radiate out these cables that come out to support. And that requires a little more math and maybe some computers to support it. So we have a couple of cable-stayed bridges in Louisiana. The first one is a steel bridge made with a weathering steel down in Luling, off the I-310, South Louisiana here, south of us, southeast of us here in Baton Rouge. And then the north of us is the St. Francisville Bridge, what they called the Audubon Bridges. They were building it, and then they called it the James John, or is it the John James? Oh, no, I got it on the next page here. So let's take a look. John first. John James. So where it came from is John and James are two soldiers that they named it after that died in the region I guess in the Second Gulf War, or I'm not sure if it was in Iraq or when it was in which location, but during that time. But anyways, but it was originally been named after the Audubon, the artist. But anyways, so it's got a long name. But anyways, this is part of the structure of it being built, and this kind of tells you how they build them. They start from the tower and they work out both ways as they add more cables, and that's how these bridges are built. The one in St. Francisville, or just off the edge at the river next to St. Francisville, the John James Audubon Bridge here, is a concrete bridge. You look at the other tower here, the Golden Gate bridges, and most of those traditional suspension bridges, they were steel bridges. And the Luling Bridge is a steel bridge. But this is a concrete bridge. It's concrete towers, and the whole structure of the deck is concrete. Yeah, the cables, they're not concrete. But the point really being is it makes it the longest. When this bridge is built, it became the longest concrete cable-stayed bridge in the Western Hemisphere, they call it. So the western half that we're in. It's a weird way of looking at it. But it supplanted the one in Vancouver area, the Fraser Bridge that I was proud of from back in the 80s. It was built somewhere in the early 80s, 1980s. So this bridge took the title away, the one in St. Francisville, because it's a longer span. It's not as tall. It's pretty close to the water here, So that's kind of funny looking because we're normally used to bridges in Baton Rouge and New Orleans being way up so that big bridges, big ships can get underneath it, but nothing but barges can go underneath these bridges like this one. Okay, well, and beyond that, I just got a sexy picture of a concrete box girder bridge here at the end here. Okay, so we are done with concrete.